Hello, MATSE 112. It's good to be with you today. Happy Monday. So I'm here at Newcastle University. I just gave a presentation on my group's work on fuel cell membranes. And so the lecture today is going to be about redox reactions and fuel cells in action. So these notes will be posted on Canvas. You can take a look at them. They give you some good background information on fuel cells and hydrogen and why it's important. And if you pay attention to this lecture, there's a couple hints that are going to help you on exam number 3 coming up in a couple days. So we'll have a lecture today, a video, and then on Wednesday I will Skype in again and we'll have a real-time review in class, and so I'll be on Hangouts. Chris will set that up, and I'm willing to go over anything you want in class on Wednesday. So you can't be shy. You need to come up to the camera and ask a question, but we'll go through things, and I promise I'll have a good whiteboard to write notes on. I'll continue to post answers to the homework and the quizzes on Canvas this week to help your studying. And remember, please email me or ask for a Skype session or anything you need, and I'm happy to review and do office hours individually as you prepare for exam number 3 on Friday. Of course, if you're not going to be here on Friday, I need to know now so you can take the exam early. Again, no late exams will be given. Same as all exams, you get a crutch sheet, so I'll tell Chris what that is. So you all have your one-page 8.5 by 11-inch handwritten sheet for the exam. No talking during the exam. You're allowed a calculator and a pencil, no phone, so we should be used to what the exam procedure is, and I'll fill Chris in as well. So don't try and pull anything over on him. All right, I'll see you live on Wednesday, but today I told you we're going to talk about fuel cells, and I'm going to give you some hints on questions that are going to be on the 3rd exam if you pay attention. All right, so fuel cells are really interesting. They were invented, or the concept of a fuel cell was invented by Sir William Grove. He's Welsh, but it's appropriate that I'm in the UK right now, because Grove is a UK citizen. And so what Grove did is he filled up glass tubes with hydrogen and oxygen with platinum electrodes. And he had a sulfuric acid electrolyte, and he called this a gas voltaic battery because these cells are filled with gas, and this is 1, 2, 3, 4 fuel cells in series. And so this is exactly what electrochemical cells look like nowadays. There's an anode and a cathode. So the anode in a fuel cell is hydrogen. The cathode is oxygen because we're doing hydrogen oxidation and oxygen reduction. We need an electrolyte. And so Grove's Wikipedia page is pretty cool because he was one of the first people to demonstrate this concept about splitting molecules into their constituent parts. And he reported his results to people you know, like Faraday, so that's very interesting. And Grove was certainly a scientist ahead of his time, and there's still the Grove Fuel Cell Symposium and the Grove Fuel Cell Award in Europe named after Sir William Grove, so I suggest you check that out. All right. One of the big issues with fuel cells is that they contain platinum. So fuel cells in general are pretty expensive. That's because they contain precious metals. And platinum is a noble metal, but you notice in this Porbet diagram, and Porbet diagrams are going to be on exam number 3, that if you look at the Porbet diagram of platinum, it's mostly in the immunity and in the passivation region. So nothing bad is going to happen to platinum. It doesn't corrode in fuel cells. However, there's this little region here marked corrosion, and these are both Porbet diagrams. It's just a little different representation. But you notice this little region right up here where we have platinum plus ions and we have an area marked corrosion. And this can be a problem because in fuel cells, as you go to very low pH and you raise the potential, and the potential of a fuel cell can be about 1 volt, you see that you have corrosion of platinum. And corrosion of platinum is not good for fuel cells. That means the catalyst is going away. Your fuel cell is corroding, and so you put all this expensive platinum in a fuel cell device and you don't get the performance that you want. It doesn't last as long as you want. So Platinum corrosion happens, again, as we go to very low pH, pH 0 or pH 1 or pH minus 2, and you should know what that means, even though you don't deal with those pHs a lot, and as you push up the potential. So this is one way that fuel cells will fail, is through this platinum corrosion, and you can see that right from the Poor-Bay diagram. All right, so I'm at this conference called Charisma, and it's at Newcastle University. Newcastle is on a river called the Tyne River, so the proper name for Newcastle is Newcastle upon Tyne, the city of Newcastle next to the river. And you can see it's very beautiful at night. So Charisma is really interesting because it's a European conference focused on fuel cells. And the EU spends a lot of money on fuel cell technology, and so this is just one of the web pages from the European Commission, but they spend upwards of $400 million, it says down here, on fuel cell research and fuel cell education. So there's a lot of big companies in Europe that are interested in fuel cells, companies like BMW, Volkswagen, BASF, Solvay, and so Europe is betting big on fuel cells as a future mobility system. They also have training programs, and so if you're interested in being trained in fuel cells, you can come to Europe, and they've got government grants to train scientists in fuel cell research, but also auto mechanics, how to deal with fuel cell cars, or people who run gas stations, how do you run a hydrogen fueling station, and so those are going to be important topics in the future. So there's lots of different fuel cells out there, it turns out. Anything from micro fuel cells to run your computer. This is a portable generator. You can buy one of these things, and there's various fuel cell cars and even a fuel cell forklift. So if they're putting fuel cells in forklifts, you can imagine that they're not an exotic topic anymore. We just need to get the performance characteristics of fuel cells right in order to put them in these different applications. And it turns out that big warehouses like Amazon and Walmart and other places where the warehouses are huge and indoors, you can't run forklifts on propane because you're putting too much CO and CO2 into the atmosphere, and battery-powered forklifts don't last for a full 8-hour shift. So it turns out that forklifts is a huge application for fuel cells, and things are picking up in that area. Fuel cells are also really popular in Japan. So this is a home fuel cell system. So this serves the hot water and power needs, and it's fueled by natural gas. And you can see these home demonstration fuel cells all over Japan. So the big governments investing in fuel cell research are the US, the EU, and also Japan are really where the leaders in fuel cells are, including the automotive companies. So fuel cells are attractive because they're high efficiency, or they can be high efficiency, and also this issue of energy density. So before we talked about the electrochemical equivalents for different metals and batteries, and energy density refers to how much energy, how many kilojoules we can have per kilogram, or kilojoules per, let's say, meter cubed. And so energy density is really important. You want energy dense fuels, or you want a lot of energy per kilogram, because you have to carry around all these things. So just like we want the most energy that we can get in our lithium-ion battery, we also want the most energy we can get in a chemical fuel. And it turns out that hydrogen has very high energy density, on the order of gasoline. So the equivalence is 1 kilogram of hydrogen contains about as much energy as 1 gallon of gasoline. So that's a very interesting comparison to make. All right, there's lots of different types of fuel cells defined by their electrolytes. So we have polymer fuel cells, we have phosphoric acid fuel cells, we have solid oxide fuel cells, and so there's lots of different materials that fuel cells are made from, and lots of different mechanisms for how fuel cells work. And I'm going to tell you about low temperature fuel cells just because the electrochemistry is interesting and easy to remember. Okay, so we also have a US government program on fuel cells. This is the office right here, and so the Office of Hydrogen Fuel Cells and Infrastructure gives a lot of grants out to do fuel cell research, like the research in my lab, and I work with these people a lot. Hydrogen is an interesting energy carrier because you can't mine hydrogen, but you can make hydrogen very easily. You can make it from natural gas, you can make it from coal, you can make it from water, you can make hydrogen from biomass, and so there's lots of ways to make hydrogen. And then we can use hydrogen very easily in transportation or distributed generation applications. And so hydrogen as an energy carrier is something that people are considering. So in the past you might have heard about the hydrogen economy, and so rather than using gasoline to carry a lot of our transportation energy, we may be able to use hydrogen in the future. And so the US government spends about $300 million a year on fuel cell research, and so this is just a schematic of where that money's going. But fuel cells will remain an important part of the energy business for a long time, along with batteries, and we'll talk a little bit about that. Okay, fuel cells were actually first used a lot in the space program. So this is a picture of the fuel cells that were used in the Gemini mission, and fuel cells are still used on the International Space Station, and when the space shuttle was flying, there were fuel cells on the space shuttle, because fuel cells, you have hydrogen and oxygen, and in spacecraft you have liquid hydrogen and liquid oxygen, and then fuel cells make water, and the astronauts would drink the water from the fuel cell stacks as it made electricity. So fuel cells have been around for a long time, but you can imagine putting this thing in your car, you need some repackaging. It's a little bit more difficult. And so fuel cells, remember, their delta G0 for the fuel cell reaction is less than 0. So fuel cells are thermodynamically favorable, just like the combustion of hydrogen. So that's really important because that's where the energy comes from. So all the thermodynamics that you know about delta G apply to fuel cells. Now there's lots of different materials in fuel cells and lots of different functions. So there's gas transport, there's water transport, there's porous electrodes, there's electrodes where the platinum lies, there's membranes, there's all the things that material scientists can handle in fuel cell devices. So it's an important topic for you to remember as you're looking for how to use your material science education. These are some pictures right here about different sorts of materials used in fuel cells, and so if you're curious as we go along in the semester, please feel free to ask me some questions about fuel cells and the materials. Okay, we can run fuel cells on hydrogen, we can run fuel cells on methanol, and so here's the hydrogen fuel cell reaction. So you should know about hydrogen oxidation and oxygen reduction. What are those half reactions? How do we sum up those half reactions to get the full cell reaction for a fuel cell? But we can also run fuel cells on liquid fuels like methanol or other types of carbonaceous fuels, and so that's something to keep in mind. So fuel cells, we're not just talking about hydrogen, there's lots of different fuels available. In fact, there's a lot of different fuels listed here, and so you have all the energy densities here for all these different fuels, and these are two mock-ups of military fuel cells. Rather than carrying around a bunch of batteries to run your targeting equipment or to run your electronic surveillance, perhaps you'd like to use a fuel cell because the specific energy density can be pretty high for these chemical fuels. The energy density of batteries is not very high at all, and so batteries are heavy and big for the little energy they carry. Now they're very convenient because it's a closed system and you don't have to pipe the fuel around, but chemical fuels actually carry a lot more energy per mass or per volume than solid state energy like batteries, and so it's something to keep in mind, and that's why people are very interested in using fuel cells as battery replacements. Okay, so there we go, the video's back on. So other than fuel cells, where we have energy that is evolved from the fuel cell reaction because the delta G of the reaction is less than 0, for electrolyzers, where we're splitting water, we know the delta G0 reaction for electrolyzers has to be greater than 0 because you need to apply current in order to split water. So you put a battery across two pencils in this case, dipped in water, and you get evolution of hydrogen and oxygen from this type of cell. This is really interesting because the first thing that people did with a voltaic pile, and if you remember, we talked about Volta, who the volt is named for. As soon as Volta invented the voltaic pile, they went and electrolyzed water with it immediately. And that's kind of cool because it shows you how important some of these processes are. It shows you how important electrochemistry is. If back in the day, before they even knew that there were molecules, they were working on splitting water and figuring out what was going on. Okay, so electrolysis is really important because if you want to fuel hydrogen buses like Proton Onsite does, which is a Connecticut company, so if you know where Wallingford, Connecticut is, you can go visit Proton and you can see their fueling station. What they're doing is taking solar energy and they're using solar electricity to split water. Then they store hydrogen and then they fill up these buses with hydrogen. So now instead of shipping gasoline around in tanks or making hydrogen pipelines or what have you, you can make hydrogen right on site and put it right into cars just from water. And it turns out we have plenty of water around, we can make plenty of hydrogen, so we're not going to cause any water shortages from this. So it's a very interesting way to think about fueling our infrastructure. One advanced application of electrochemistry is called this CO2 electrolyzer. You can see it right here, and there's some really interesting things that are possible with CO2 electrolysis. So instead of splitting water into hydrogen and oxygen, you can take CO2 and perhaps you can make formate or you can make CO. And from formate or ethanol or methanol or CO, you can make lots of different chemicals. And so this is really interesting because you can get fuel and chemicals now from the air if you can accomplish CO2 electrolysis. It turns out this is an important research area. We know how to split water. That's done in large scale, as I showed you with fueling hydrogen buses. But this is the next frontier where now we can make gasoline directly out of the air if we can electrochemically convert this CO2. Now you know that CO2 to fuel, you know what the sign of delta G is going to be for that, right? So delta G reaction is going to be greater than 0 because this is definitely uphill. So it takes a lot of energy in order to convert CO2 back into fuel because you're very familiar with the opposite reaction. You know that you take fuel, you oxidize it, and the delta G is negative. You get power from that. And so it's really important to line up your spidey sense. Am I applying power or am I getting power back with what the delta G is and how that affects these different processes we're talking about. And of course we can run a fuel cell on CO or formate or something in the reverse reaction. So just like we have reversible hydrogen fuel cell and water electrolysis, we can have a reversible CO2 electrolysis or a fuel cell that runs on carbonaceous fuels. So we're going to talk a little bit about hydrogen to wrap up the lecture, and I'll give you some resources, and then you can continue studying and asking me questions for exam number 3 as you get ready this week. So number 1 lore is fuel cell or hydrogen is dangerous. And this is a picture of the Hindenburg, and the reality is yes, hydrogen is dangerous, especially if you have an aluminum skin that's filled with rubber, like the Hindenburg, not the Heisenberg. I've been watching too much TV. But hydrogen is dangerous. It's a fuel. It's an energetic fuel. But the reality is, so is gasoline. And so people have looked at this and they've compared 2 cars. One car is filled with hydrogen, one car is filled with gasoline, and what they did was that they ruptured the gas tank in each of these cars and looked at the resulting explosion. So you can see in hydrogen, you have this big hydrogen flame. You know, it looks pretty impressive, but in a couple seconds, it's gone. The hydrogen burns out very quickly and disperses. But in gasoline, it's just getting going. And the problem with gasoline is that it burns and burns and burns. It'll burn the whole car down. So eventually you see this big conflagration of this car whereas the hydrogen fuel cell car doesn't have any hydrogen in it anymore, but it didn't cause a big explosion. So that's something important to remember, is that lithium-ion batteries are also dangerous. There's been lots of fire from those, and so any energy source any source of concentrated energy is going to be dangerous. We just need to know how to handle it. The next fuel cell lore is fuel cells are expensive, and they are, especially when they contain platinum, but think of all the things that were expensive back in the day, like computers. There used to be only a couple computers in the world, and they were enormously expensive. But I've already told you that fuel cells are being put into forklifts, and you can imagine that if fuel cells are going into forklifts, they can't be that expensive. So this is a utilitarian tool. There's millions of forklifts in warehouses all over the world, and so if fuel cells are making their way into forklifts, they can certainly go into automobiles and other applications that we're interested in. And you see here's a diagram of the cost, and so the cost of fuel cells is the cost per power, so we're getting down to on the order of $30 per kilowatt power. And so if you work on cars, you can buy a crate engine for $4,000 or $5,000 from your favorite engine manufacturer, and we're getting there on fuel cells, where now you can buy a fuel cell with that equivalent power of that engine for $10,000 or $5,000. And so fuel cells, the cost is coming down, just like the cost of electric vehicles, just like the cost of hybrid vehicles. And so that's a important point I want to make, is that some people think that batteries are better than fuel cells. So if you read about electric vehicles, perhaps you've heard fuel cells called fool cells before. But the reality is that we need a hybrid system. So we need both a battery and a power unit that can generate energy from chemical fuels. Right now we have a Prius. A Prius has a battery, and we put gasoline in the Prius, and a hybrid electric vehicle is a really smart way to go, because you can refuel it quickly, and then the internal combustion engine can charge the battery, and basically we have an electric car. The next generation after gasoline hybrid electric vehicles is fuel cell electric vehicles. So you're filling up fuel cells with hydrogen, or fuel cell cars with hydrogen, and that hydrogen is charging the battery and electric infrastructure in a battery vehicle. We know that Teslas don't have a long range, and Leafs and other fully electric vehicles really don't have a very big range. We can get the range with a chemical fuel like hydrogen or gasoline, yet still have all the benefits of a battery-based vehicle. And so we think that in the future, and some governments think in the future, that we're going to have both an electric hybrid, maybe fully electric vehicle for in-town use, and then we'll have a battery fuel cell hybrid to take advantage of this chemical fuel, primarily hydrogen, because we know that hydrogen doesn't give off any pollutants where it's combusted. Certainly if you make the hydrogen from methane, you can get CO2 that way, but perhaps if you make it in a plant, you can capture that CO2. Of course, if you're making hydrogen from water, it's a very clean process. It just costs you a little bit of solar energy. And so I hope I've given you some idea as to how fuel cells, and hydrogen will be used in the future. Now, if you paid attention to this video, you've probably seen a couple answers that are going to be on the third exam. So remember, the third exam is going to cover electrochemical redox reactions. So is the delta G positive or negative? Do you want high energy storage or high voltage or high electrochemical equivalence in your system? And how might Porbet diagrams be important in some of these processes, and what are Porbet diagrams all about? So hopefully that gives you a couple hints on exam number 3, and feel free to ask me questions by email or on Canvas. And if you're interested in fuel cells and want to do some reading, there's a bunch of good books on fuel cells, and so I suggest you check them out. Fuel cells are a great material science problem, and they'll be an important topic in your future career, hopefully. Okay, please keep those questions coming. I'll check in with you live on Wednesday, and have a good Monday. Thank you very much. Bye-bye.